Organic chemistry is the branch of chemistry that deals with compound containing carbon atoms. But at first, it was thought that organic compounds are those which are obtained from living things. Vitalism, or commonly known as vital force theory, says that those compounds which are obtained from living organisms are organic, and those obtained from non-living are inorganic. But later on, this theory was rejected mainly by Friedrich Wohler when he prepared urea, which is an organic compound from ammonium cyanate, inorganic in nature. After rejection of vitalism, the modern definition of organic chemistry was put forward, and now we say those compounds that contain carbon are organic in nature. Organic compounds are mostly complex and have large molecular structures. This is due to the fact that carbon has a unique ability to form long-chain compounds, and this is known as catenation. Actually, catenation is the ability of a carbon to form long-chain compounds, which is unique, and none other than carbon atom can form such long-chain compounds. Classification of organic compounds. Organic compounds are classified into two categories, which are open-chain or acyclic compounds and closed-chain or cyclic compounds. Open-chain organic compounds are a type of organic molecule in which the carbon atoms are arranged in a linear or branched chain rather than forming a ring structure. These compounds are also known as acyclic compounds. Key features of open-chain. Organic compounds include linear or branched structure. The carbon atoms are connected in a straight line or in a branched manner. They can be further classified based on the type of bonding between carbon atoms, such as alkanes have single bond between carbon atoms. Alkenes have at least one double bond between carbon atoms, and alkynes have at least one triple bond. Closed-chain compounds, also known as cyclic compounds, are organic molecules in which the carbon atoms are connected in a loop or ring structure. Unlike open-chain compounds, these have no terminal ends because the chain of carbon atoms forms a closed loop. Key features of closed-chain. Organic compounds. Ring structure. The carbon atoms are arranged in a ring or cyclic pattern. The rings can be simple, like in benzene, or fused, like in naphthalene. Closed-chain compounds are further classified into two categories, allocyclic compounds and aromatic compounds. Those cyclic compounds that resemble aliphatic compounds in their properties are called alicyclic. Examples include cyclohexane and cyclopropane. But aromatic compounds are those that contain at least one benzene ring in their structure, and most common examples include benzene and naphthalene. To understand organic chemistry, it's very important to have knowledge of functional groups. Actually, functional group can be defined as the atom, or group of atoms, or double bond, or triple bond, whose presence gives specific properties to organic compounds. Now let's explain it a bit more. When all the carbon atoms contain only single bond, we call them alkanes, and those which contain at least one double bond are known as alkenes. So actually it's single and double bond, which is creating difference between alkanes and alkenes, and that's called the functional group. There are many other functional groups such as alcohol, formyl group, ketones, and carboxylic acids. Functional groups play a crucial role in determining the properties and reactivity of organic compounds. For example, alcohols can undergo oxidation to form aldehydes or carboxylic acids, while alkenes can participate in addition reactions. Isomerism refers to the phenomenon where two or more compounds share the same molecular formula, but differ in their structures or spatial arrangements. These different forms are called isomers. Isomerism is significant in organic chemistry because the structure of a molecule largely determines its chemical properties and reactivity. There are several types of isomerism, the most important of which include structural isomers and stereoisomers. Structural isomers have the same molecular formula, but different connectivity of atoms. This means the atoms are bonded together in different ways, leading to different structures. It is further classified to chain isomers, differ in the arrangement of the carbon chain. For example, straight chain and branched chains compounds. Position isomers differ in the position of a functional group on the carbon chain, and functional group isomers differ in the type of functional group present. Geometric isomers are a type of stereoisomerism, where the isomers have the same connectivity of atoms but differ in the spatial arrangement around a double bond or a ring structure. It is also called cis-trans isomerism, and this occurs when two substituents are on the same side known as cis-isomer, and on opposite sides called trans. In 2-butene, the cis isomer has both methyl groups on the same side of the double bond, while the trans isomer has them on opposite sides. Stereoisomers have the same molecular formula and connectivity of atoms, but differ in the three-dimensional orientation of their atoms in space. Hybridization is a concept in chemistry that explains the mixing of atomic orbitals to form new hybrid orbitals. These hybrid orbitals are crucial for understanding the bonding and geometry of molecules. The type of hybridization influences the molecular geometry, bond angles, and overall shape of the molecule. Some common types of hybridization are sp, sp2, and sp3. In sp hybridization, one s orbital mixes with one p orbital from the same atom to form two equivalent sp hybrid orbitals. The remaining two p orbitals remain unhybridized. The two sp hybrid orbitals arrange themselves linearly to minimize electron pair repulsion, leading to a bond angle of 180 degrees. In acetylene, each carbon atom is sp hybridized, forming a linear structure with a triple bond between the carbons and a single bond between carbon and hydrogen. In sp2 hybridization, one s orbital mixes with two p orbitals to form three equivalent sp2 hybrid orbitals. The third p orbital remains unhybridized and is often involved in pi bonding. The three sp2 hybrid orbitals arrange themselves in a trigonal planar geometry with bond angles of 120 degrees. In ethene, each carbon atom is sp2 hybridized, leading to a planar structure with a double bond between the carbons and single bonds with hydrogen atoms. In sp3 hybridization, one s orbital mixes with three p orbitals to form four equivalent sp3 hybrid orbitals. The four sp3 hybrid orbitals arrange themselves in a tetrahedral geometry with bond angles of 109.5 degrees. In methane, the carbon atom is sp3 hybridized, resulting in a tetrahedral shape where each sp3 orbital forms a sigma bond with a hydrogen atom. Structure and bonding. The molecular formula represents the actual number of atoms of each element in a molecule. It does not provide any information about the arrangement of these atoms. For ethanol, the molecular formula is C2H6O. The structural formula provides more detail by showing how the atoms are connected or bonded to each other. It represents the molecular structure using symbols for atoms and lines for bonds. For example, structural formula of ethyl alcohol can be written as: organic reactions typically fall into several main categories such as addition, substitution, elimination, and rearrangement. Each type of reaction involves different processes and has distinct outcomes. Addition reactions occur when two or more molecules combine to form a single product. This type of reaction is common in unsaturated compounds, such as alkenes and alkynes, where a p bond is broken and new s bonds are formed. For example, the addition of hydrogen to ethene in the presence of a catalyst forms ethane. This is known as hydrogenation. In substitution reactions, one atom or group of atoms in a molecule is replaced by another atom or group of atoms. These reactions are common in saturated compounds, like alkanes and aromatic compounds. For example, nucleophilic substitution reactions in which a nucleophile replaces a leaving group in a molecule. But in electrophilic substitution reactions, an electrophile replaces a hydrogen atom in an aromatic ring. The reaction of chloromethane with hydroxide ion to produce methanol is an example of nucleophilic substitution. Elimination reactions involve the removal of a small molecule from a larger one, typically resulting in the formation of a double or triple bond. These reactions are the reverse of addition reactions and often occur in saturated compounds. For example, unimolecular elimination. The reaction proceeds via a carbocation intermediate, and bimolecular elimination, in which the reaction occurs in a single step.